A special Feynman technique. Okay, so we have an integral from 0 to 1 of x to the power p minus 1 Lix dx. If you don't know about the Li function, Lix dx is basically integral from 0 to x of 1 by ln of t dt. Yes. Please don't be confused with the big Li function, which is something different. Yeah, big Li function. It also has subscript, let's say p. This is sum from n equals to 1 to infinity of x to the power n by n to the power p. Yes. And the small Li function is defined as this integral. Now in this video we will just find the Mellin transform of this function. Yeah. Okay, so for that let us substitute Li with this definition. Integral from 0 to 1 x to the power p minus 1, and then again integral from 0 to x of 1 by ln t dt. Okay, so now let us try to convert the limits of integral into numbers. Yeah, because that will be easier to deal with. So we have y equals to t by x substitution. That will change this to integral from 0 to 1. Yeah, integral from 0 to 1 x to the power p minus 1, integral from 0 to 1 by ln of t is xy. Yeah, and over here after it's also dx over here. Now dt is x dy and dx as well. Yeah. Now let us make this as a double integral from 0 to 1, integral from 0 to 1 x to the power p minus 1 by ln of xy. Even if we understand the order of integral, it will still be the same difficult integral. Yeah, it wouldn't really simplify a lot. And there is x over here, dy dx. Yeah, it don't really simplify a lot. So like the only way we can remove this ln xy in the denominator is to introduce e and then use Feynman's technique. Yeah, let's introduce I of t as integral from 0 to 1, integral from 0 to 1 of x to the power p. This is actually x to the power just p, and e to the power minus t times ln xy by ln xy. If we make this sense, and now if we differentiate with respect to t, we see that the ln xy in denominator is going to get cancelled. Yes, and that's a great boon for us. So let's differentiate with respect to t. We have integral from 0 to 1, integral from 0 to 1, and then we have x to the power p, e to the power minus t ln of xy times minus ln of xy by ln of xy. Yeah, and then dy dx. Okay, now this cancels out. Yeah, we can take minus sign outside, so we get I dash of t as negative of the integral from 0 to 1, integral from 0 to 1. Over here it's x to the power p, and then this is basically xy to the power minus t. Yeah, and then dy dx. Now this is a very easy integral, everyone can solve it. Yeah, now I dash of t is negative of the integral from 0 to 1, integral from 0 to 1. This is x to the power p minus t. Yes, y to the power minus t, and then dy dt. Now we can integrate this to separately, x in one integral and y in the other integral. Yeah, we can do that. Negative of the okay, so negative of the integral from 0 to 1 x to the power p minus t dt, and the integral from 0 to 1 y to the power minus t, and not dt, this is dx, sorry for that. this is dx, and this is dy. Yes. Okay, now radius of t is this over here is just negative of basically 1 by p minus t plus 1, yeah, and this one is 1 by 1 minus t. Yes, am I doing it correct? Yes. Okay, now let us try to change this to partial fractions. Yes, if we try to change this to partial fractions, let us see what we get. Radius of t would be negative of the, now for 1 minus t, just substitute t over here. So if we substitute sorry, no, for 1 minus t just substitute 1 over there, so p minus some percent, so 1 by p, and plus for p minus t plus 1 you need to substitute p plus 1, yeah. Substitute p plus 1 over here, you get 1 by 1 minus p plus 1, so that is minus p, yeah. Okay, so now I of t will be basically minus 1 by p, and its integral will be ln of 1 minus t by minus 1, yeah. Minus over here will be plus 1 by p, and its integral will be ln of p minus t plus 1 by minus 1. Yes. Okay, now we are really close to the answer. Just let us do some simplifications. ln of 1 minus t by p minus ln of p minus t plus 1 by p. This is the final result, but I of t is not what we are expecting. Also, there needs to be a plus c over here. I forgot that. Now, first of all, let us find the value of plus c, and then we will proceed. To find c, we just have to know that when t is infinity, this integral goes to 0. So I of infinity is 0, and the required answer is basically when t is 0. When t is 0, we get the required integral, yeah, that we are searching for. So let us use the I of infinity is 0. I of infinity will be, from over here it will be just 1 by p ln of 1 minus t by 1 minus t plus p, yeah, plus c, yeah. Now if t goes to infinity, this will be equal, so ln of 1 will be there, and we know that ln of 1 will just be 0. 0 times 1 by p is 0, plus c, we see that c is actually 0. Yes, therefore you can say that I of t is 1 by p ln of 1 minus t by 1 minus t plus p. Yes. Okay, nice. Now we need to find I of 0, yeah. Now I of 0 is 1 by p ln of, now wait, there are zeros, so 1 by 1 plus p. Yes. And now this is minus 1 by p ln of 1 plus p, which is the answer. Let's check. Minus 1 by p ln of 1 plus p. Minus 1 by p ln of 1 plus p. Yeah, that's the answer. So the main twist over here was to introduce this expression e to the power minus t ln of xy, which would basically cancel the expression and just make it simple. Yeah. So that was the main idea. All there's just partial fractions over here. And just the definition, nothing more. Yeah. Just this was the main idea. And they use Feynman's technique. So that was it. Hope you enjoyed the video. Thanks for watching, and look forward to seeing you in the upcoming videos too.